Start. So in the last class we started talking about chance or probability. As I mentioned, I have deviated a little bit from the book because I wanted to be a little bit more mathematical. So we discussed, I defined an event mathematically as a subset of a sample space. So any event we should be able to define as a subset of a sample space. But that definition like that is not always necessary to calculate probability, but anyways an event can be defined as a subset of a sample space. Now when you want to calculate the probability of an event, there are several methods that we can use depending on the conditions we have. The earliest method that many people used, or earliest people used, was called the classical method or the a priori method. So that actually can be calculated only under certain restricted conditions. What are the conditions that we have to use this method? First of all, our event must have come from a sample space which is finite. Our event must be a subset of a finite sample space. And then the second condition is that all the outcomes in our sample space must be equally likely. Right? So those are the two main conditions. But again, as I mentioned in the previous class, to decide whether the outcomes are equally likely is somewhat difficult for some people. One reason for that is actually, again, when you talk about equally likely, there is again a probability idea, right? So in order to define probability, we have to use again the same idea. So that's a circular type of problem, but that is anyway, that is the way it has been defined. So if those two conditions, so what we have to do is actually we have to think whether there is any reason to believe otherwise, right? Whether there is any reason for us to believe that some of the outcomes are more likely than the other. So this is just a guess actually most of the times. So if you have those two conditions, then you can find out the probability of your event using the classical method. But practically in most of the situations what we use is this method, relative frequency method. Using this method we can calculate the probability of some event using the data. As for the previous method, actually we didn't want the data, we don't want to carry out the experiment. Only thing we have to know is what the sample space is, and then how many items in the sample space and how many items in the outcome. As I forgot to mention that the probability in that case in the classical method is defined as the number of outcomes in our event divided by the number of outcomes in the sample space. Right? So because we are dividing by the number of outcomes in the sample space, this number must be finite, otherwise we cannot define that probability. So when you go to the relative frequency method, what we are using here is actually an approximation to the actual probability of an event. This is coming from this definition of the probability. Right. So again, you are considering an event A must be a subset of some experiment, some sample space. So for that sample space there must be some experiment. So if our experiment can be done again and again and again, in that kind of situations, we can actually calculate the probability by carrying out the experiment large number of times. According to the definition, is the probability of event A is equal to the number of times event A occurs divided by the total number of times we do the experiment, as the number of experiments goes to infinity. So it's defined as a limit, right? When you do the experiment, in each experiment either our event occurs or doesn't occur. So therefore we can count at each step, at each experiment, we can count the number of times our event has occurred, divide that by the number of times the total number of times the experiment has done. So that is called the relative frequency of our event. Right? So this number changes with n. So when n goes to infinity, it usually converges to some fixed number. Right? So that number is called the probability of event. So, but practically we cannot do the experiment infinitely many times. So what we do is we do it as many times as possible, and then at that value, at a large value of n, we just calculate the relative frequency at that point. Right? How many times event A has occurred divided by the number of times the experiment was done. Right? So that gives you an approximation. If n is large enough, that will be a good approximation to the actual probability. So therefore, in order to get the probability using this method, we need the data. Actually, we need a relatively large data set. Otherwise, the estimate will not be good. Right? So that is a weakness of this method. But anyway, many people use this method most of the times. Right. So as this picture shows, when you carry out the event, here, for example, I have calculated the relative frequency at each n, where n is the number of times that you have carried out. You can see at the beginning there was a big variation in the relative frequency, but as n goes to 1000, 10,000, maybe later on, it will come to this line. Right? So that whatever this line value is the actual probability of the event. But see, if you, for example, if you did the experiment only 200 times, you will stop it here. You will take this value as the, whatever this value as the probability of the event. So it will be somewhat different from the actual value. Right? But if you stop at the 800 level, then in that case your estimate of the probability will be this value here. So that is much closer to the actual value than what it was at 200. So that's why we say do the experiment as many times as you as possible. Right. And then the next method is subjective method. That is usually, as I mentioned, in order to apply the relative frequency method, you should be able to carry out your experiment again and again and again. Only in that kind of situations, that method is possible. But there are situations where we want to talk about the probability of some event as a result of some experiment which can be done only once, right? For example, maybe deciding the winner. We want to find out what is the probability that Sri Lanka will be next World Cup, for example. So there will be only one World Cup in that whatever the year. So we cannot do it again and again and see how many times Sri Lanka win and divide by. So that's not possible. But still, people are interested in talking about the possibility or probability, right? So in that case, we use something called the Bayesian method or subjective method, but that is actually not in the scope of our course. Therefore, we will not talk about that. And the next method that we will be actually talking a little bit in this class is actually the model-based. So in the model-based case, actually we will be dealing with something called random variables. In this case, we have to define something called random variables. Up to this point, we were only talking about events as a subset of the sample space. Right? So in that case, we are considering every event as a subset of some sample space. But when you use this model, we look at the events, because we always calculate the probability of events, but we write down the events in another way. Actually, we write down events using something called random variables. So I'll come to that part later. So once you define your event using a random variable, we assume some probability distribution for your random variable, like a normal distribution that we already have. Right? There are so many other models that people use depending on the shape of the distribution of your random variable. And we know a lot of mathematical properties of those man-made models. So therefore we can use those known properties to answer questions like calculating probability, calculating some other quantiles and so on. So that is the other method. Right. So for this method and the relative frequency method, for both we need data actually. In the relative frequency method, if you want to get good estimates, you have to have a very large sample, because the probability of our event will converge to the actual value or will be close to the actual probability when n is large only. Right. The advantage of this method is probably you can answer the same questions that you have, for example, calculating probability with a smaller number of observations. For example, if you are considering a certain situation, like for example, if you want to find out what is the probability that say weight of a certain person selected from a certain population will be less than some value. Right? If you are interested in what is the probability that the weight of a person, male for example, less than 50 kilos. Right? So that is so weight is less than 50 kilos is the event that we want to look at. So we want to find out the probability. One thing we can do is we can randomly select individuals one by one and measure their weights, right? So when you measure the first person, his weight may be 60 kilos, so our event has not occurred at that time. In the second case, so you have relative frequency 0 divided by 1. Right? And if you look at the second person, he may be 45, so your event has occurred at that point. So at that point, relative frequency is 1 divided by 2. So you stop there and say, okay, but the probability that the person is less than 50 kilos is 1 over 2. That is wrong, right? So you have to look at large number of people, measure, and then see how many people were less than 50 kilos and divide by the total number of people. In order to get a good estimate of the actual probability, you have to have a large data set, large sample. On the other hand, if you assume that the weight of a person has some distribution, if you assume a certain model like a normal model, right? If you assume that weight of a randomly selected person has a normal distribution, so in order to talk about a normal distribution, you need two quantities always. Right? What are the two quantities? We have to know the mean, we have to know the standard deviation. If you know the mean and the standard deviation, at least approximately, of course these are always going to be approximations, because in real life there are no situations where your random variable will exactly have a mathematical model like normal model or gamma model or any other model. Right? So these are always going to be approximations. So you need to be able to estimate the mean and the standard deviation to a certain accuracy. For that you don't need 100 observations or 1000 observations, maybe 30 or 50 will be enough. So if you get those two estimates for the mean and standard deviation using a data set rather smaller than the required by the relative frequency method, then you can assume that okay, weight is normally distributed with this mean came from a sample of this 50 and standard deviation came from the same sample. And then we can find out the probability using like how you already know how to calculate the probability of a normal distribution, standardizing and so on. Or you can use a computer, right? There are so many packages nowadays. Once you assume a certain model, you can calculate in probability using a computer. Right? So therefore that method is much better than the relative frequency method. On the other hand, there is a difficulty because assuming a suitable model is difficult, right? If you have assumed a wrong model or not suitable model, then all the calculations will be wrong, right? So therefore, for a given situation, you should be able to get a good idea, have a good idea, maybe from some previous research, what would be a more suitable model for that kind of variable, or maybe from maybe you're having a sample. Again, if you have a histogram, you can get a good idea about the shape. But in order to get a histogram and then get a good idea, you need a large sample, right? 50 may not be enough. So all these weaknesses and advantages and disadvantages are there in this model. So depending on how many observations you have, depending on how much prior information you have about the suitable models and so on, so you can select one of these methods. Right, so that's how you usually calculate probability, right? Either using classical method or relative frequency method or modeling method. Then we discussed the axiomatic definition. As I mentioned, this definition is not helpful in calculating probability. It's helpful in not defining any function as a probability function. Right. So if you have a mathematical function and if you check whether you can use that as a probability function, then of course these axioms have to be satisfied. Right. So now we will look at some examples, because you asked me about these counting techniques last time. So I thought maybe I should include some counting techniques and look at some examples for the classical method. Because if you are using the classical method, always you have to calculate or find out the number of outcomes in your event, and also the number of outcomes in the sample space. So that means you have to count the numbers in two sets, right? Your event and sample space. So therefore we need some mathematical rules, for example. So those are usually called counting techniques. So I have just written down here a few counting techniques, like the ways, number of ways a certain event can occur, right? If you say a certain event A has 5 outcomes, that means event A can occur in 5 different ways, right? If one of those outcomes happens in an experiment, then you say your event has occurred, right? So let me look at these few rules. There are so many other rules, but most often used ones are these ones. So the first one is just giving you the number of ways a certain event can occur. So suppose you are interested in a certain event, but suppose you can consider this event as combination of several other events. So your event A is a combination of A1, A2, A3 and suppose several events. And suppose you know how many ways A1 can occur, how many ways A2 can occur and so on. If you know individual number of ways in each component can occur, then the total number of ways the whole event A can occur is given by this rule. Right? So if one sub-event can occur in one ways and the other one can occur in 2 ways and so on. Suppose there are k components. So then the total number of ways your particular event can occur is equal to n1 times, n2 times, n3 times, n4 times up to nk. So for example, let me just take a simple example. Suppose you are preparing an ID. You want to have an English letter here, and suppose you want to have 2 numbers here, digits in the ID, right? So 2 numbers followed by an English letter. Right? So if I ask how many ways, how many different IDs can you make? Right? So this ID, making ID is actually composed of 3 things: selecting a letter, first letter for the first place, and digit for the second place, selecting a digit for the third place. So that will give you. So how many ways that you can select English letter for the first place? 26 ways. Right? Suppose the numbers can be repeated. Any number can be anywhere. I mean, zeros can be anywhere like that. There is no restriction, for example. So in that case, for the second place, selecting how many ways can you select a digit from the second place? Okay. There are 10 ways. For this also, then 10. So if you don't have any restriction, then the total number of different IDs will be 26 times 10 times 10 total number. Right. If you say, for example, okay, digits cannot be the same, then how many different ones we are, which don't have the same digit repeating, like 5, 5, 1, 1, 2, 2, and so on. So in that case, still for the first place there are 26 choices, 26 ways. For the second one, there are 10 ways. Once you select this one, it cannot repeat, here. So therefore, there are only 9 ways for that once. So therefore, the total number of IDs with different digits will be like that. Right? So in order to find out the ways, number of ways happening that kind of events, you can use that rule. Right. And then the second one, suppose you have n items which are different n items. Each is different from each other. Second one talks about how many arrangements of all items. If you take all items, how many ways, different ways can you arrange them? Right. So all these are different items. So you are considering like you are filling n boxes. Right. So the first box, second box, third box, and so on. The nth box. Right. So one arrangement will be like filling n boxes. So how many ways that first here the first box can be filled? N. Right. So there are n ways. Once you fill one, you can there are n minus 1 ways for this one. Right. So n minus 2 like that, and then for the last one there will be only 1 way remaining after that. So therefore, according to the first rule, the total number of different arrangements will be equal to n times n minus 1 times up to 1, which is the same as n factorial. So if you consider n items together, all the items, there are factorial n factorial different arrangements. So those are called, that's a kind of a permutation, n out of n. And then more general one, if you, okay, so that is this one. What is this factorial notation? This is just the factorial notation. Right? You already know that. And then if you have n different items, and if you are selecting R and arranging them, you have n different items, you randomly select R items and then arrange. How many different arrangements like that? That's the question. So it's like now there are only R places to fill. Right? First place, second place, up to R. So the first place there are n ways. For the second there are n minus 1 places and so on. For the last one, n minus R minus 1, right? For the second n minus 1, so for the third n minus 2, so for the R and then n minus R minus 1. Right? So therefore the total number of ways will be the product of these n times, n minus 1 times, n minus 2 times up to this value. Right? So when you take the product of those, that has a notation, short notation. Right? The value is given by that, but it is denoted by NPR, number of permutations when R items taken together, right? That's NPR, and that mathematically we can prove that is the same as factorial n divided by n minus R factorial, because this is like 1 to up to n multiplication divided by, you have to remain these numbers, so then all the other numbers have to be cancelled out. So therefore numbers up to 1 from this number should be, we have to divide by that. So what is this number here? So you can say that is equal to 1 to R, and then times R minus 1, so R plus 1 and R plus 2 times n. So this is factorial n, and up to rth.
R is less than n, so
Yeah, r is less than equal to n. Yeah, so this we need the product of these ones. So we have to have. Okay, let me write down 1, 2, 3 up r here, and then r plus 1, r plus 2, r n. So that we can write down as the factorial layer. N minus r factorial will be what? N minus r, n minus r minus 1, n minus r minus 2. So some of these will cancel out with this one, and then you remain with this. Then n minus r minus 1 is like that one through into make a make only capital. So so it's NPR. Number of permutations when R items are taken from n different items. And the next one is the number of combinations. That is number of ways that you can select. Right? Earlier, number of ways that you can select and arrange. So for example, in that case, A and A, B and B and A, B, A will be considered as two different ones. Once you have, for example, two letters. If you have three letters, A, B, C, A, C, B, C, A, B, all these will be considered as different ones in permutations. But in combinations, A, B and B, A are considered as the same, only one, right? So, how many combinations? When you take a permutation, R items, right? So, how many ways that R items can be arranged?
R factorial.
Yeah, R factorial. So, when you come to the combinations, you have to divide the number of permutations by R factorial, because there are R factorial items which have the same items in different order. So, when you take the combination, we take all of them as one. So, there are R factorial ways of arranging the R items where you have selected. So, any arrangement is taken as one. So, therefore, the number of ways that we can selections will be equal to NPR divided by R factorial. NPR divided by factorial, this is equal to NCR. Right. Number of combinations, some people say number of choices, choose R. So it is the same as N factorial, R factorial, N minus R. Right. So that is the difference between those two. And then the last one is suppose you have several groups of items. For example, suppose there are three groups, maybe some three colors, right? In a box there may be 5 red ones, 3 white ones and 2 black ones. So similar ones, different numbers. And then if you take all of them and arrange, how many different arrangements? That is given by this number. Suppose, for example, there are k groups. In the first group there are n1 things. In the second group there are n2 things, and so on. In the kth group there are nk things. n1 are similar, n2 are similar, and so on. Then the total number of arrangements is given by this. How do we get that? If all the arrangements items were different, then there are factorial number of arrangements. Right? But there are n1 similar ones. n1 similar ones. So those n1 can be arranged in n1 factorial times. So all those be taken as 1. So therefore this has to be divided by that to make all those to be 1, and similarly there are n2 similar ones. They all can be arranged in n2 factorial ways, so you have to divide by that also. This number has to be divided by that to make those 1 and so on. So each number of these you have to divide the total number by the product of each number of ways of arrangements. That's how you get that. So those are the commonly used counting techniques. Right? When you want to use classical probability and then to find out how many ways your particular event can occur and how many items in the sample space, how many outcomes in the sample space, you usually use those principles. So let's look at a few examples. Shall we try these ones now? Given those rules, shall we try? This is the same example that I looked at earlier. A security supervisor of a large corporation wishes to issue each employee an identity card with one English letter followed by 2 digits. Right, so the same scenario that we have earlier. Right. So this has to be a digit, this has to be a digit, this has to be a letter. If an identity card is selected at random, what is the probability that 2 digits are different? Right. That means what is the probability of getting an identity card with 2 different digits? So how do we find out that? First of all, we have to see now, we have to check whether the classical probability can be used or not. Right? So the total number of ways, that is total number of different ID cards as we saw earlier, is 26 times 10 times 10. They each is different. Right? So therefore that many different outcomes in the sample space, they all are equally likely. Right? They all are having 1 over whatever that number chance. They are all equally likely. So then we have to divide the number of events that a particular event can occur by that number to get the probability of this event. So how many ways can we have an ID card with 2 different digits? 26 times 10 times 9. So therefore the probability of getting 2 different digits will be equal to 26 times 10 times 9 divided by 26 times 10 times 10. So it's okay. Similar to that, can you try the other ones? So the second one actually you can do 2 ways here. Because the previous one you can get from that one also. In the previous one 2 digits are different. Now this is the complement of that one. The numbers are the same is complement of 2 digits are different case. Right? So therefore one way to find out is 1 minus the previous probability. 1 minus the previous probability, or you can directly find out how many ways you can have the same digits, right? So, how many ways can you have the same digits? 26 times?
26 times 10 times 1.
Why 1?
Because once you pick the first digit, already the second digit has to be the same, so there's only one chance.
No.
Because you can't
Now
make it.
they have to be the same, no? Like 1 1 you can have, 2 2 you can have, 3 3, 4 4, 5 5, 6 6, 7 7, 8 8, 9 9, 0 0. So there are not 1. You said 1.
I said 26 times 10 times 1.
10 times 1. Yeah, yeah, that's correct. Now you don't have to even consider three cases here. You can consider those two as one thing. So in that case, like, so that's okay, correct. Yeah. 26 times 10 divided by the total number of ways.
So can we say 1 over 10?
Sorry?
1 over 10 as the probability.
Yeah, you get 1 over 10, right? Yeah. Yes. Because you have 26 times, as he said, 10 times 1, or you just say 10 because 1, 1, 2, 2, 3, 3, there are only 10 days. So then here 26 times 10 times 10. So it's 1 over 10. The third one, the probability that the first digit is not 0. First digit is not 0. So the number of ways you even can have is 26 times. The second one, there are only 9 possibilities. But for the third, you can have 0 also. Therefore, there are 10 possibilities. Divided by 26 times 10 times 10. What is the probability that it contains 5? Contains 5 means maybe one number can be 5 or both numbers can be 5. It has to contain. So how many ways can have 5?
2 times 26 times 9
Why 2?
plus the first digit can be 5, that's 26 times 9 again, the second digit can be 9, so 26 times.
Yeah. Is that clear? Or you can simply just look at part by part. If you want, for example, you can consider how many ways the first number can be 5, how many ways the second number can be 5, how many ways both can be 5. You just add them up, right? So then that will be the same answer. So 20, the number of ways that the first number is 5 ways. This is only one way here. First number has to be 5, and then second number can be. For example, suppose we are considering all possibilities, so then there are 10 possibilities. So 5, the second 5 is included here. අපි ගන්න අමතක කරන 9යි. අරක වෙනම කරමු. පහ පහ කියන වෙනම. මෙතන 9යි. දෙවෙනි එකෙත් ඒ වගේ, right? Here 9 times 1, and then there we have to add 1, 5, 5. Right? So 20. That is 26 times 1. Not, yeah, 26 times 1. Yeah. So that is the total number of ways you can have 5. And then you have to divide them. Right. What is the probability that it contains A and 5? A and 5. So the first number must be A, first letter must be A. Right. So then that means the previous numbers, all the previous numbers you divide by 26, right? Total number. Right, so that is just 1 times that. So then it has to be divided by the total number of the sample space. Right. Okay, so let's look at this example. A box contains 3 white balls and 2 black balls. A sample of 3 balls is taken randomly from this box. What is the probability that the sample contains 1 white ball, 2 white balls, at least 1 white ball? So here, first of all, we have to think a little bit. In the previous case, all the possible cards were different. Right, all the now here is going to be somewhat, there are similar balls. So you have to think whether you can write down these events as a subset of some sample space where, of course, the number of outcomes will be finite, but whether we can look at a sample space where the outcomes are equally likely. Right? Can we write down these events as subset of a sample space where the outcomes are equally likely? That we have to look at. So if you can write down like that, then classical method can be used. So how would you write down? There are different people may write down the sample space different ways. For example, one might just consider the how many balls are selected?
Three.
3 balls. Yeah. So some might say just the color, right? So therefore, one might say WWW, right? Black, black, black. W, black, W, like that. Some people write down a set of colors like that. That is one way to write down. But if you write down like that, outcomes will not be equally likely. Outcomes will not be equally likely because there are more white balls than black balls here. Another person might write down the number of black balls, for example, in the sample, or number of white balls in the sample. So if you consider number of white balls in the sample, it can be 1, 4, 2, 4, 3. So one might consider this as the sample space. When you write down the sample space like that, the first event is just containing 1. But you cannot use the classical method because these outcomes are not equally likely. You can write down your event as a subset of that, but classical probability method cannot be applied because they are not equally likely. So the question is that, can you somehow, making some assumption, write down the outcomes so that the outcomes are equally likely? If we can write down these events as subsets of this our sample space, then we can apply the classical probability.
W1, W2.
Yeah. As in the previous case, we have to somehow make individual outcomes completely different outcomes. Right? Otherwise,
Are the balls taken together or one at a time?
actually that doesn't matter. Right? One by one is, you can assume that you take one by one, and in that case you can also consider the order also. Assume, right? Doesn't matter, right? Or just say the 3 balls come. You can consider the sample space without considering the order of the 3 balls, or with considering, because any 3 can be arranged in the same number of ways if you consider them as different balls. W1, W2, W3, B1, B2, if you consider like that, each ball will be considered as different balls. That can be arranged in 3 factorial ways, 6 ways. And it's either if you want to write down the sample space, you can write down the sample space considering the order, that means considering the permutations. Or you can consider the sample space considering the combinations. Permutations, combination, the sample space containing the combinations will have 1/6 of the number of items in the permutations, because each 3 can be arranged in 6 ways, 3 times, 2 times 1. So whatever the way you can consider, anyway we have to, first of all we have to consider each ball as different. So therefore we have to assume that we mark them or somehow distinguish them as 3 different balls, white 1, white 2, white 3, black 1, black 2, and so on. So if you assume like that, then the outcomes can be, for example, W1, W2, W3. So the sample space එක කියනකොට මේ තුන එකක් කියලා ගත්තොත් ඔක කොහොම ලිව්වත් කමන්නේ. Just selection. Or if you consider the permutations, you can write down this in 6 ways also. Combinations how many ways can we have one white ball? How many ways can we have one white ball out of 3? Right? So one white ball means one white ball and 2 black balls. Sample as having one white ball means having one white ball and 2, because we are taking 3 now. So therefore our event can be considered as a combination of 2 things. You have to have some certain number of ways to have one white ball, certain number of ways to have 2 black balls. So how many ways can you select one white ball out of 3 white balls? Suppose this is just white and black. Right. You just consider the selections without considering the order. How many ways can you select one whiteboard out of 3? There are 3 ways, right? So there are 3 ways of coming one whiteboard. Then there are 2 blackboards, right? So 2 blackboards can come from 2 blackboards only one way. So therefore, the total number of having one whiteboard is 3 times 1. But how many different samples can you have? In order to calculate the probability, you need to look at the total number of ways having any sample with 3 items. How many ways, without considering the order, how many ways can you have 3 things out of 5 things? 5 different things. That is 5C3, just combination, selections. So therefore the probability will be 3 divided by 5C3, that is 3 divided by 10. If you answer the same question considering permutations, there were 3 selections, 3 ways to select one whiteboard. But if you consider the number of permutations, for each of these there will be 6 ways, so you have to multiply by 6, right? 6 times 3, 6 permutations. And when you divide by that, again that number has to be divided by 6. So that 6 cancels out. That's what happens. So therefore you can consider the number of permutations or number of combinations. Usually considering number of combinations is easier. So similar way, can you find out the probability of having 2 whiteboards? So there you have to consider the number of ways of having 2 whiteboards out of 3 boards divided by the total number of ways having any 3 boards. So that is equal to, again like filling 2 boxes, right? You have to have a black and white. So there you need 2 blackboards here and 1 white. Right? So how many ways you can have here?
2 whites and 1 black.
2 white, yeah. 2 white and 1 black. So how many ways can you have 2 whites? 3C, 3C2 ways, 1 white,
1 black.
1 black.
2.
So the total number of ways of having this kind of sample, considering the combinations, is equal to 3C2 is 3 times 2, that is 6. You have to divide that by, again, 5C3, divided by 5C. The probability is 3C2 times 2 divided by 5C3. At least 1 blackboard. What do you mean by at least 1 blackboard?
Either 1
Yeah, 1 blackboard, exactly 1 blackboard, or exactly 2 blackboard. That's all you can have. There are 2 blackboards. So you have to add all those possibilities. How to have exactly 1 whiteboard and number of ways of having 2 blackboards divided by again 5C3.
It is the same as the first and second.
1 whiteboard.
Addition.
Yeah. Okay. So I want you to answer this question by yourself. from this, I need this. How many ways? How many ways this particular event can occur? That in order to happen, these 3 women have to come from these 7 women. These 2 women have to come, 5 men, right? In this case, actually, theoretically, like in the previous case, if you want, you can consider permutations. But in this particular case, permutations will not be practically meaningful because you just are interested in the committee. No? You are not considering the order anyway. So therefore, just considering the selection is practically also meaningful. So the number of ways of selecting 3 different women from 7 is equal to 7C3 times then 5C2 divided by 7C
12C.
12C or 12C. Or to the 12 that out of that 5. Right. So this is the same situation earlier, but somewhat different problems. A box contains 3 white balls and 2 black balls. 2 balls are taken one after the other without replacement. 2 balls are taken one after the other without replacement. What is the probability that the first ball is white? What is the probability that the second ball is black? What is the probability that the first ball is white and the second ball is black? Let's try. So again, if you want to consider the sample space as having equal chances for all possibility, each possibility, you have to just assume that you have labeled them W1, W2, W3, and B1 and B2. So the total number of ways of selecting 2 balls will be equal to total number of ways of selecting 2 balls will be equal to what? 5C2. 5C2 altogether 5 balls. Right? If you assume that they are labeled, right? So 5C. So that will be the denominator in the probability. So numerator terms you have to calculate how many ways the first ball is white. So there are 2 balls, first and second one. First ball can be white in 3 ways. Right. Second ball, first ball is white. Second ball can also be white or black in that case. Just say first one is white. Right. So therefore, how many ways for this? Once one ball, one white is come.
But sir, you don't have calculate the second possible.
Yeah. In this case, you don't even have to, right? You are interested in only the first one, right? First one. Second one can be anything. So there are all the other possibilities, right? You don't even have to calculate. If you want, you can calculate like that, and then of course. So first one is white. There are 3 ways. Therefore, 3 divided by 5C2, that is 10, 3 divided by 10, right? What is the probability that second ball is black? So it's very similar to the same thing, right? You are only considering second. So second.
Taking into account that the two balls are taken out,
One after the other.
You can't take 5C2, right? Just
Without replacement.
So it should be 5 into 4, right? First ball it's 5, second ball.
Yeah. You are correct. I made a mistake. 5 times 4. Because the first one, there are first one 5 ways, and for the second one, there are 4 ways. It's not 5, 20. I made a mistake. Yeah, so what is the probability for the second one then? The second one is black.
I used another method.
Hmm?
I used this method. So
Oh no, that's okay. Doesn't matter. What method you are using is okay, but this method will be difficult if you have a large number of votes. That's the thing. So, what is the answer for the second one?
3 into 2 plus 2 into 1 divided by 5 into 4.
How is that?
First one white, second one black, plus second one, first one black into second one.
So the first one can be anything, black or white.
Yeah.
Second one has to be black, right? So the second one, if you just look at the number of ways again, second one has to be black. So there are 2 ways. Black ball. Once you have selected one black ball for here, you have how many? 4 other possibilities. There are 3 white balls and 1 black here, but there is another black. So that also can come, isn't it?
Without replacement, they are choosing the first ball.
Without replacement, yeah. Once you have selected that, there are the others
So
are there.
either there is only 1 ball or 2 balls, so not sure the public.
So there are altogether 5 balls.
Yeah.
So for now we want this to be a black. So there are 2 ways for that to happen. Right? B1 or B2. If B1 comes here, this can be W1, W2, W3, B2. Any of those. There are 4 ways. Right? If B2 comes here, then that means this can be anything all the others, isn't it? Right. So therefore, 4 times 2. Right. Once you have selected one for here, there are 4 other choices for here. So the total number of ways you can have 2 black balls here is 4 times 2. Total number of ways all these things can happen is 5 times 4, 20. So that divided by 20. If you take with replacement, that is a different.
Yeah, it was the same answer, but method.
Different method, yeah. Yeah. Then the third one, what is the probability that the first ball is white and the second ball is black? First ball is white, so there are 3 choices for this. Once you have selected for that, anyway, the second one has to be black, no? Second one has to be black, so therefore only 2 choices here. Right. So this 3 and 2 choices. So 6 divided by 20. The probability. So if you are doing the same thing with replacement now, total number of ways of selecting 2 will be 5 times 5. So that will be in the sample space. For the first one there are 5 choices. For the second also 5 choices because you are putting it back. So 5 times 5. So the first one is white. There are 3 choices, 3 down. So the probability is 3 divided by 25. And second board is black. There are 2 possibilities, but for this one there are again all 5 possibilities. Because you are putting it back once you have taken. So 10 divided by 25. So similarly, you can answer the other question. Okay. Now this is a more practical situation. This is something called like counting a certain number of animals in a certain closed area. This is called capture-recapture experiment. Here we are trying to calculate a certain probability, but the same idea we use usually to estimate the number of animals in a certain population also. That's we don't discuss it here. So let's look at this problem. There's a certain population. Suppose there are wildlife population involves capture. In this experiment, an initial of m animals is captured. Each of these animals is tagged and then returned to the population. After allowing some time for the tagged animals to mix into the population, another sample of size simple n is captured. Yeah, this simple n is smaller than the previous capital N. Suppose that the total number of animals in the population is n. What is the probability that the sample contains x tagged animals? So you have a situation like this. There are altogether n animals. Out of them, m animals are tagged. M animals are tagged. So non-tagged, there are n minus m animals, altogether n animals. So we take a random sample from this. Sample size is simple n. Let us denote the number of tagged animals in the sample as x. So tagged animals, this is n here. So this is non-tagged. So therefore n minus x non-tagged animals. So the question is asking what is the probability that the sample contains x tagged animals. So this is a situation where we take a sample without replacement. So generally when we say take a sample, that's what we mean without replacement. Right? So having the probability of having x tagged animals is the same as having a sample with x tagged animals and n minus x non-tagged animals. Right? So can you get the expression for the probability of getting x tagged animals? It's a mathematical expression rather than number.
Simple x over capital N.
Simple x over?
Capital N.
Not really. These x must come from this m because there are only m number of tagged animals. Right? In the whole population, we first catch m animals, put a tag on them, and then put them back to the population. Right? Allow them to mix, and then after some time, you take another random sample of size n, and then count how many animals in that sample has tags. So x is the number of tagged animals in the second sample. Right, so what is the probability of getting this kind of sample from this procedure? That is the question. Right. So having this kind of sample means getting x animals from m, this m, and getting this many animals from this. So, right, so therefore the number of ways of having this kind of sample is equal to the number of ways of getting x animals from m times the number of ways of getting n minus x animals from these animals. Right? So this is like one event, but it is composed of two things. Like first thing can occur in a different number of ways. Second event part can be happen in another way. And therefore, the total number will be the product, right? So therefore, it has to be mcx times n minus mc n minus x. That is the total number of ways this kind of sample can happen, divided by total number of ways any type of sample of size n can occur. That is equal to, right, it's coming from the whole n, and here simple n. So the total number of ways of having simple n out of capital N is equal to n c n. So that is the probability of getting X tagged animals from this experiment. We use this idea to estimate. Now here we can calculate this probability. If you know all these numbers, you have to know n, x and n. Right? If you know the numbers, you can calculate the probability. But we use this idea to estimate the number of animals in a closed population. For example, certain particular species of fish in a lake or small pond or something if you want. Right? So you can do this kind of experiment easily. Right? You don't know how many that kind of species fish in the pond, but you can first catch certain number of animals of that species and put some tag on them, put back, and then after mixing you can take another sample. So in that case what we usually do is this. We know the m, right? We know the initial sample size. So we know n, we know how many we catch in the second sample. And we can count how many tagged animals in the second sample. In that case, we will know x also. Right? So what we will do is we will assume different values for capital M. Usually it has to be a bigger number than capital M. No? So just take some number larger than m, assume that number for capital N, put that number and calculate this probability. Right? So in that case you will be calculating if there are that many animals in the, that many fish in the pond, what is the probability of having X animals, because we have already observed X animals. What is the probability of happening what we have actually seen here? We can calculate that. And similarly take another value for n. Right? If for example earlier we assumed 100, now we assume 101. If there are actually 101 fish of that particular species, what is the probability of happening what we have observed already? Right? So like that what we do is we will calculate the probability of happening what we have already observed. So that is the probability that say x is equal to simple x. We have already observed that, where capital X denotes the number of particular type of fish in our sample. And suppose we have seen that it is equal to 10 already, so we are can calculate the probability that x equal to 10, assuming different values for n. Different values for n. So when you calculate, usually this will have this kind of picture. Usually there will be a point where this probability of happening x equal to 10, that is what we have already observed, will have a highest probability for a given some value of n. So in that case we take that value n as our estimate for the total number of that kind of fish in the population. So that's how estimate. Because we have observed already something, and we look at what is the value of n that gives the highest chance of happening that. And then that's called the method of maximum likelihood, and this probability is called the likelihood of happening our event. So that's one method, and this idea is used there. Okay. මේක උදාගන්න බෑ වඳුරු estimate කරන්න නම් රිලා we close conversation oh මේ දුවනවා කොහොම estimate කරාද මම දන්නේ I don't know what they used to estimate the number of nobody gives the total details, they just give the numbers. Anybody can say any number, no? I wanted to find out how they did it and whether it is a reasonable method or not, but I was not able to find out at least how they did it. Okay, so let's look at this program. A production facility employs 20 workers on a day shift, 15 workers on a swing shift. I don't know what swing shift is, but 10 workers on the graveyard shift. 3 shifts: day shift, swing shift, and graveyard shifts. So, day shift, swing shift, graveyard. 30 here. Sorry, 20 here. 15 and 10. Employees. A quality control consultant is to select 6 of these workers for an in-depth interviews. 6. Take 6 out of this whole population. Suppose the selection is made in such a way that any particular group of 6 workers has the same chance of being selected as does any other group. Right, so, just like drawing 6 slips without replacement from out of all 45, right, all 45 people are different. What is the probability that all 6 selected workers will be from the day shift? What is the probability that all 6 will be from the day shift? How many total number of ways of selecting? First of all, we look at the number of ways in the sample space. Number of ways of selecting 6 people. How many total number of ways? 45 C 6. So that's what we have to divide by any to calculate the probability. So what is the what are the how many ways you can select 6 people from the day shift? So that means all these people 6 should come from this 20. Right? So 20 C 6 divided by that gives the probability. What is the probability that all 6 workers will be from the day shift, same shift? So that means either all are from this, or all are from this, or all are from this. So how many ways can that happen?
26 plus
20
15.
C6, yeah, plus 15 C6 plus 10 C6 divided by the previous. What is the probability that at least 2 different shifts will be represented?
At least 2 different shifts, 35 C6, 25 C6.
That there are 2 ways to find out. One is easier way, the other one is different. So you can look at the, for example, coming from this and this, coming from this and this, coming from that and that. So that is 2, at least 2. That means you have to consider all 3 also, right? There is an easy way.
Yeah, 1 minus 20
Yeah,
C6
because
minus.
having at least 2, representing at least 2 shift is the complement of having the coming from the same shift, right? So therefore, once you have calculated the probability they are coming from the same shift, you have to just take 1 minus that probability to get the
So if we consider the first way,
sorry.
if we consider the first way of doing that without 1 minus the probability,
First way means,
by selecting 2 at a time and
yeah, you can have 2 at a time, or maybe all 3 may be there. At least 2 represented means 2 is represented, or all 3 is represented.
yes, if all 3 is represented, that would be 45C6.
No.
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 Yeah.
No.
That includes everybody from
two only 2. So you can මේදක පමණක් සහ මේදක පමණක්. ඒවයි අයිති වෙන්න ඕනේ වෙන්න පුළුවන් ආකාරයකට. ඊට පස්සේ තුනෙන් වෙන්නත් උනේ. ඒ කියන්නේ තුනෙන් වෙනවා කියනකොට ගන්න ගියාම ටිකක් අමාරුයි නේ. ඔව් විවිධ ආකාර වලට ඉන්න පුළුවන් තුනේ. ඒකට ඒ ඔක්කොම සලකන්න. ඒකට ඒක ගොඩාක් අමාරුයි කැල්කියුලේට් කරන්න. ඒක මොයි මේකකින් හේකුයි මේකකින් දෙකුයි මේකකින් තුඩුකුයි වෙන්න පුළුවන් මේකකින් වරන් විවිධ එකක් කරලා. එතකොට හරි අමාරු නේද? ඉතින් එතකොට ඒ නිසා මේ අරක තමයි ලේසියෙන් වෙන්නේ. Right. Okay, so those are some examples. Actually, these kind of problems are not very practically useful, right? Very rarely practically useful, but mathematically interesting. So that's why I told the other day that classical method is very rarely used in practice, because it has a very strong restriction that all this the event must come from a sample space where the outcomes are equally likely. Right? So only if we can write down our sample space in a way that, and then our event can be taken as a subset of that, then only we can apply that method. Right? So now we will look at some examples for relative frequency method. Shall we take a small break and then